We have learned the Hamilton-Jacobi method in the last two lectures, but you see when we actually construct the Hamilton-Jacobi equation, it would be nice if you could solve that equation and get your Hamilton's principal function or Hamilton's characteristic function, and then the solution seems immediate. But the problem here is in fact solving Hamilton-Jacobi equation is in fact really hard. In fact, it is notoriously hard. Probably for most problems you may not be able to actually solve this, and that is when you take recourse back to your Lagrangian or Hamiltonian formulation to construct the differential equations and solve those. But there is one situation where this Hamilton-Jacobi method or procedure becomes useful is when you can use separation of variables. Remember, you probably are already aware of method of separation of variables. If you for example have a Laplace equation, and Laplace equation is a partial differential equation for electrostatic potential, and it has three independent variables, and if you could separate this into three ordinary differential equations, then of course the solution becomes easier. And it is possible to employ separation of variables in this case too. Okay. Wherever the system is separable, then of course things become easier. Okay. So, let me start by defining the meaning of the separability. So, if a variable or a variable q j, we will call it separable if we can write the principal function s, Hamilton's principal function s, in two terms. One of the terms will depend only on q j, and the other term must be completely independent of q j. Then we say variable q j is separable in Hamilton-Jacobi equation. Now, I would for example take q 1. So, if I can write this Hamilton's principal function in two terms, two additive terms here, if I can write that such that S 1 depends only on q 1 here, and S 2 does not depend on q 1 at all. Okay. In that case, we say q 1 is a separable variable. Okay. Now, if I can do same thing for each of those variables starting from q 1 to q 2 and up to q 1, then what happens? Then of course, the system is very easy to solve. In that case, your Hamilton's principal function will look like sum of the individual pieces, and each individual piece S I will depend only on q I and not on any other variables. And in this case, what will happen to the Hamilton-Jacobi equation? You should be able to separate the Hamilton-Jacobi equation into several parts. One part or one ordinary differential equation for each I, for each q I. Okay. So, this is what will happen. The Hamilton-Jacobi equation now, which is just one single differential equation, which is partial differential equations with n plus 1 independent variables, now boils down to n partial differential equations, but with just two variables q and t, okay, individual q I and t. Fine. Can you do the same thing for the Hamilton's principal function? Suppose Hamiltonian is independent of time t, then we know that we can actually do better job with Hamilton's characteristic function, w function. In this case, we will say if q 1 is cyclic, then I should be able to write the w function in terms of two pieces. Okay. Now, a priori it is very difficult to say which of those will be separable unless you actually examine the structure of the differential equation. But for some cases it is very easy to see. If for example, a variable is cyclic, say q 1 is cyclic. Okay. If q 1 is cyclic, then we can definitely separate that out. Here I have written the Hamilton-Jacobi equation for the characteristic function w. Now, let us assume that q 1 is cyclic. If Q1 is cyclic, then we already know that P1 is a constant of motion. So, what I am going to do is here this is in fact function of Q2 to Qn, and then there are these partial derivatives, but this particular partial derivative we know is a constant number. Okay. So, I can put that as a constant. Fine. So, I can now separate the characteristic function W into two pieces, one piece which depends only on Q1 and the other piece W prime which depends on the remaining variables. Okay. Now, we know that this one is constant. So, the differential equation here, the Hamilton-Jacobi differential equation, that will depend on Q2 to Q1, partial derivative of W with respect to Q2 and all the way up to Q1 and that constant gamma. Okay. However, that just appears as a constant in the equation. And now, what we can do is W1 is very easy to solve. This in fact is exactly equal to, so the first part here can be easily written as W1 because P1 is partial of W1 with respect to Q1. Now, and I have set it equal to gamma, I can immediately integrate this and I can get W1 which is gamma times Q1 which is P1 Q1. And see, this is in fact expected. I wanted to shift or transform to a new coordinate system where the new canonical coordinates are cyclic, but Q1 is already cyclic. So, I really do not need to change this one. So, in this case the new momentum capital P1 will be small p1, and in fact that is what will go here as P1 Q1. And what is this? This will in fact generate the identity transformation for Q1 variable. Okay. Fine, Q1 P1 pair. And what goes in the Hamiltonian-Jacobi equation now is, so we have already determined W1, the Hamilton-Jacobi equation now is the equation in W prime, remember, and then you solve it. And can you sort of keep on doing this procedure? If for example, two of them are cyclic, then you can go ahead and write capital W as some W prime plus P1 Q1 plus P2 Q2, okay, and this will work. What if all of them are cyclic? Oh, then we really do not need to do anything because that is exactly what we were trying to aim for. Okay. Fine. So, when you can do this separation for all variables, then we will also say that this is a completely separable system, and if it is a completely separable system, then all the coordinates are already cyclic, there is not much to do here. The interesting case would be when n minus 1 coordinates are cyclic and 1 is not, then of course, things are easy. Fine. The best way I can actually explain this method is by taking an example. Okay. So, let us do a problem of central force potentials. The Hamiltonian here, so what I am going to do is in the central force problems, remember the potential energy is function of the distance of the particle from the origin. So, that is the distance or the coordinate r in spherical coordinate system. So, it would be better if I use spherical coordinate system here. So, I will write my Hamiltonian. So, your coordinates here are r, theta and phi. Okay. Now, the corresponding Hamiltonian is p r square plus p theta square by r square plus p phi square by r square sin square theta, and plus of course, whatever that potential is, but remember that potential does not depend on theta and phi, the angles. Now, theta of course appears here. Since theta appears there, it is not cyclic, but phi is cyclic. So, one possible separation is immediate and straightforward. If you look at phi, then your p phi will be constant of motion. We will set it equal to some alpha phi, and then your W phi, the piece in the Hamilton's characteristic function which depends on phi, we will call it as W phi, will simply be given by alpha phi into phi, where alpha phi could be written as also p phi. Fine. Now, look at how the separation goes. Here, what I am going to do is write the Hj equation by putting W first, okay, the full characteristic function. Then substitute Pr here, substitute Pr by partial derivative of W with respect to r, same for theta and same for phi. So, the equation now looks like this. What I am going to do is rearrange this equation in such a way that all the phi terms are on one side. So, write it like this: take this term to the right hand side and take this r square sin square theta back to the left hand side, and then take this 2me also to the left hand side, leaving you with r square sin square theta into all these terms as they are, and there will be 2m v minus e, and this will be equal to minus of del w by del phi. And at this point I will put in the ansatz. Ansatz is, I will write w, which is r theta phi, as two pieces. One is w1 which depends on r and theta, and w phi which depends on only phi. And if I put now this back into this equation, remember, because w phi is only function of phi and w1 is independent of phi, when I take derivative of w with respect to phi, it is exactly same as w phi partial of w phi with respect to phi. So, what will happen to this part of the equation? This is in fact nothing but partial derivative of w phi with respect to phi is equal to constant alpha phi. And why would I set this equal to constant alpha phi? Because remember, this side now will acquire, this will become w phi, and on this side you will have w1. Remember, w1, w phi does not depend on r and theta. So, on this side you have w1 which is function of r and theta. See, now your left hand side contains only terms in r and theta, and right hand side of this differential equation contains only terms in phi. And remember, these are independent variables. So, the only way this can be true for all values of r theta and phi is individual side of this equation must be equal to some constant, and we cleverly choose that constant to alpha phi square with a minus sign, okay? And that gives me this. So, this is in fact the way separation is done, okay? Even though I have given a formal definition earlier, it is actually inspection of the differential equation will allow you to decide whether you can separate variables or not, and in this case we can actually separate the phi variable easily. And also phi variable was cyclic, so we knew that result already, and if phi is cyclic or if any variable is cyclic, then I can separate it very easily. What about the separation between r and theta? Oh, that also can be done. See, now look at the equation with left hand side of the Hj equation. So, now you have differential equation which is in terms of w1. So, this is differential equation for w1, and w1 is function of r theta. And now rearrange this too. It is possible to do that very neatly, and if I rearrange this, then I will take this partial derivative of w1 with respect to r plus 2m v minus e. This term also depends on r, remember v depends on r, and on the right hand side I will write it as 1 over r square and a bracket here. Okay. Now, w1 still is function of r and theta. So, I make another ansatz that w1 is function of is sum of two terms which is wr and w theta, wr depending on only r, w theta depending on only theta. And in that case, partial derivative of w1 with respect to r is same as partial derivative of W r with respect to r and partial derivative of sorry, I should write W r. Let me correct that. So, partial derivative of W 1 with respect to r is equal to partial of W r with respect to r. Same thing is with respect to theta. Partial derivative of W 1 with respect to theta is same as partial derivative of W theta with respect to theta. So, what will happen to this? This W 1 here can be replaced by W theta and this W 1 here can be replaced by W r. Okay. Now, you again have got separation of variables. If I take this r square to the right hand side, then I have to the left hand side, then I have left hand side which depends only on r and the right hand side which depends only on theta. And then again by the same argument, this must be true for all values of r and theta only if each of these sides must be equal to some constant. So, I am going to put it equal to, again a clever choice, in the sense we already know the answer. So, we can preempt the choice of this particular constant. So, I will put this as a square of alpha theta and with a minus sign. Okay. Now, you can separate this particular Hamilton-Jacobi equation into two parts. One is for the right hand side. So, the right hand side is equal to the constant, that is partial of W theta with respect to theta squared plus alpha phi square divided by sin square theta plus alpha theta is equal to alpha theta square, and same for r. So, I have rearranged them in a neat nice looking form. So, that what have we done here? We started with a single partial differential equation for W which depends on three independent variables r, theta and phi, and then separated these into three separate ordinary differential equations which are first ordered there. So, three first order differential equations, and that too ordinary differential equations, but not the partial differential equation. So, this is the power of separation of variables here. Now, what I am going to do is for the same problem, but with a specific case with a Kepler's problem 1 over r potential. I am going to show you one example where we can calculate the frequency of the periodic motion from the action angle variables method. Okay, fine. So, basically it is a continuation of this problem, but now I am going to choose the potential energy to be the 1 over r potential. So, let us start with the Kepler's problem. Here the Hamiltonian is given by p r square plus p theta square by r square plus p phi square by r square sin square theta, and plus now the potential energy we are going to choose it as an attractive 1 over r potential. So, that comes with a minus sign and there is 1 over r. Now, we already know the solution to this particular case. Remember, the motion here is periodic. See, when I say periodic, I do not really mean it is just periodic in time t. We know that it is periodic in time t, it repeats, it is a closed orbit and it repeats in time t. But in addition, it is also periodic in angle phi, it is periodic in coordinate r, it is periodic in angle theta. So, the motion here is in fact periodic in all three variables. Now, it is a rotation kind of motion in angle phi, because remember in the orbit it just goes around the origin, which means the phi angle traces out values from 0 to 2 pi coming back to the same point, and then it keeps on doing that. Whereas, in r and theta it is an oscillation kind of motion. Remember, there are the two turning points and your r actually oscillates between the two turning points. And what about theta? Theta too is actually oscillating between 2 points which probably are symmetrically placed above the xy plane. So, this is the idea we already have. So, we can safely use action angle variables for all 3 variables here. Okay. So, the function Hamilton's characteristic function, we will write it as 3 pieces, and now what is p phi? P phi is nothing but partial derivative of w with respect to phi. In the previous slide we have already seen that we can set it equal to some constant alpha phi. Then p theta is nothing but partial derivative of w with respect to theta, and again look back at the previous equation. I can rearrange this and write it as alpha theta square minus alpha phi square by sin square theta to the power half. And the last equation, which is for r, is again del w by del r can be taken to the left hand side, everything else can be pushed to the right hand side, and then you get the equation for p r. From these 3 variables, p phi, p theta and p r, I can construct the action variables. Now, the action variables would be, your j phi is of course very simple, it is integral of p phi d phi, and it is, remember, it is an integration over one cycle. But what is the cycle here? For phi, the cycle is just 0 to 2 pi. Okay. Now, for the theta integral, again remember there is a integration over one cycle, p theta d theta, but we already know the value of p theta from the separation. So, we already have that, and same thing for j r, which will be defined as integral p r d r, and then that is equal to square root of 2 m times E minus V and plus alpha theta square by r square. Now, before I proceed, we of course can, so there are 3 constants of motion here. One is E, which is basically the Hamiltonian is constant of motion, and we set it equal to E, and we also know that that is the total energy of the system or energy of the particle in this case. Alpha theta, if you now compare this expression for P r, what is alpha theta? Oh, that would just be the total angular momentum, it will be magnitude of the total angular momentum. And what would be alpha phi? Alpha phi would be angular momentum of the the component of the angular momentum which is along the z axis. See, look at the figure here, we are not assuming here that the motion is planar, it probably is not planar, we do not know before solving the problem. So, first of all we are going to assume that the trajectory is in 3 dimensional space. So, now you have angular momentum which is pointing in any direction, in which case I will assume that your angular momentum is pointing in n cap direction here. Okay. And if that is a constant of motion according to this, then we know that the motion is planar, and then we again will not make an assumption that the motion is only in xy plane, but it could be a tilted plane, tilted with respect to xy plane. Okay. So, the first integral of course is very straightforward, because the angle phi varies from 0 to 2 pi, that is one cycle, and integrand is just constant. So, I will do that integral straight away, it is going to be 2 pi times alpha phi, it is the integral of this. Okay. Now, look at the second integral, the theta integral, that is slightly tricky, slightly longish, but we will do this one in small steps, okay, in a very detailed way. So, I will start with this. Now, let me define this new angle I as cos of I as alpha phi by alpha theta. Remember, then I will be of course a constant, because both the alphas are constant. What is this I? Even though a priori we did not know, we just need to do this integral, but since we already know the answer to the problem, I can interpret these particular values there. I, remember, alpha phi is a magnitude of the z component of angular momentum, and alpha theta is a magnitude of the total angular momentum. So, what would be the ratio of these two? So, the cos I angle or I angle is angle between z axis and the total angular momentum. So, that is in fact this axis here. Remember this angle here. Remember, we have taken your L vector, the total angular momentum vector along n cap there. Okay. So, what would be the tilt of the plane? The tilt of the plane is of course given by this angle here, and I will call this angle as theta naught. And you can immediately see from the geometry that the plane of the orbit is perpendicular to the angular momentum. So, the angle between z axis and the orbit, the plane of the orbit, that is going to be theta naught, which is pi by 2 minus I. Okay. Now, what happens to this angle theta? Now, if you look at the diagram very carefully, so what we are going to do is this: the plane of the orbit suppose cuts your xy axis, sorry, xy plane in a line which is ON, this line here, ON line. Okay. Then if you choose a perpendicular to that, that would be your topmost point, that will be the highest z coordinate, that also will be the smallest theta naught, smallest theta, and will be equal to theta naught. And as this particle goes down, remember it is going to go to the other side and come back like this. So, as it goes down, by the time it comes to n, what happens to the theta variable? It reaches pi by 2, and then it goes down to symmetrically to pi minus theta naught, then comes back to pi by 2 and to, so the motion of theta is basically oscillatory between theta naught and pi minus theta naught. Okay. Now, let us do some straightforward algebra, basically a couple of substitutions, so that we can integrate this. Now, define the new variable sin psi, which is cos theta by sin I. Remember, this is also same as cos theta by cos theta naught. Now, the derivative of this will be cos psi d psi will be equal to minus sin theta d theta divided by sin I. So, basically I want to change variable from theta to psi. Now, what are the limits of psi? Remember, your theta varies from theta naught to pi minus theta naught, which means it goes from plus 1 in this case here to minus 1, because we are dividing by cos theta naught there, which means your psi goes from pi by 2 to minus pi by 2 and back to plus pi by 2. While doing that, it will of course go through the 0 2. Now, what is this 0? Basically, that is the angle with which ON makes. That is when theta is equal to pi by 2, your psi will be equal to 0. So, it is a now oscillation in psi, which is from 0 to pi by 2. And because it is symmetrically placed, I am going to actually integrate only one portion of this, say pi by 2 to 0, and then multiply it by 4 times to get the total integral around the cycle. Okay. So, now your integrand here, this integrand can be recast in this form. You take alpha theta out, then this will become sin square theta cos square I into cosec theta d theta. Okay. That is basically d theta over sin theta. And now put d theta back into this equation, and this would become alpha theta is equal to, so what I have done here is basically you write cos square I as 1 minus sin square and sin square theta as 1 minus cos square theta, and that one would get cancelled to rearrange it in this way, and then substitute for psi and you would get, so basically if you substitute this term here comes to cos psi, then you get another cos psi from the transformation of the differentials, that gives you cos square psi, and then you have divided by sin square theta, and sin square theta I am going to write it as 1 minus cos square theta, and cos theta again back in terms of sin psi. So, finally, your integrand looks like this here, and this integrand is integrable. Remember, because the limits of integration now is from 0 to pi by 2. Earlier, remember, we actually wrote it as pi by 2 to 0, but then there is one extra minus sign which allows you to interchange the limits. So, finally, your j theta integral will become 4 times. Remember, 4 times because I am integrating only one section of the 1/4 of the trajectory, and the integration is from 0 to pi by 2. On this side here, this integration is doable. There are many ways in which you can do this. So, one of the standard ones would be you probably can put u is equal to tan psi and write this integral in terms of u, in which case the limits for u will be from 0 to infinity, and this integral now should be able to, you should be able to do without any problem, and that actually comes out to be 2 pi alpha naught times 1 minus cos I. And look at what is cos I there. Cos I is nothing but alpha phi by alpha theta. So, if I put that there, this would be 2 pi times alpha theta minus alpha phi. Okay. Remember this, j theta is equal to 2 pi times alpha theta minus alpha phi. But do you remember what was 2 pi times alpha phi? That was just j phi. Okay. So, your alpha theta is nothing but j theta plus j phi by 2 pi. Okay. Now, this is the consequence. If I now look at the third integral, the R integral, then I now have integral of 2m into e minus v plus alpha theta square divided by sin square theta. Okay. And the cycles are like this. You go from R1 to R2. What is R1 and R2? Remember, all you have to do is look at this particular integrand. There is a square root. Okay. So, there will be turning points, that is when the quantity in the bracket would become 0. For those values of R, you have a turning point. Okay. So, your R actually goes from R1 to R2 and R2 back to R1. Remember, the sign of PR is actually different in different sections. When you go from R1 to R2, PR is positive. When you come back, PR will be negative. Okay. Now, look at what will happen to this. In this case, the alpha theta here is nothing but sum over j theta plus j phi. Okay. So, what will happen is this, your Hamiltonian is energy E. Okay. So, when I do this integral here, when I complete this integral here, and which I have written here, but I will still make a point before I go to that equation, E will contain j phi and j theta as a combination, because remember only alpha theta appears in this equation and alpha theta is nothing but j phi plus j. So, when we wanted to express Hamiltonian in terms of these 3 action variables j theta, j phi and j r, these two j theta and j phi, they appear together as a sum with coefficient equal to +1 for each one of them. And now, the frequency of the rotation about phi or rotation of phi angle and the oscillations of theta, they are given by derivative of h with respect to j phi and derivative of h with respect to j theta respectively. But if you look at this expression for h, since they appear exactly in the same way, these two frequencies will be equal. So, by the time phi does 2 pi or particle goes along a trajectory completing the phi angle from 0 to 2 pi, your theta has gone from theta naught to pi minus theta naught and back. That's exactly is a statement that your orbit is a planar orbit. Both of them are actually having the same frequency. And finally, you of course can integrate this. Once you integrate, you can get this. Okay. This integral is actually a standard one. You will get a quadratic equation. The standard substitution here is putting u is equal to 1 over r, transform it to new variable u, and it is a standard integral for square root of a u square plus b u plus c. Okay. You can do that by looking at the table of integrations, and the final answer comes to this. And now I am going to write this E. So, it is a Jr is equal to minus of j theta plus j phi and plus pi k times square root of 2m by E with a minus n. Remember, I forgot to mention this right from the beginning. Remember, if E is positive, then you do not have a periodic motion in everything. For periodic motion for all three r theta phi and bounded motion, I need E to be negative, and that is exactly what is shown here. If E is negative, that minus sign makes sense. Okay. Finally, I will write E as 2 pi square divided by into mk square divided by, this is interesting, it is a sum of Jr plus j theta plus j phi whole square. Not just Hamiltonian appears as a combination of j theta and j phi, but it actually is sum of all three. The Hamiltonian depends on each one of these action variables in exactly same way with the same coefficient. What does that mean? The frequency of oscillation of r, frequency of oscillation of theta and frequency of rotation of phi, all these are equal. That is it. See, all frequencies are equal. And what is the meaning of that? The orbit is not just planar, but by the time r does that oscillation from r1 to r2 and back to r1, your phi has done a rotation of 2 pi. What does that mean? It is in fact just a simple closed curve with exactly one minimum and one maximum in r. So, it ought to be a loop which is convex, and that in fact will turn out to be the ellipse. Of course, it is special for 1 over r, but it will turn out to be ellipse. And great thing about this is I can now write down the time period of the oscillation, which is 1 over frequency, and that is nothing but you can take del E by either to get the frequency, I can calculate del E by del j r, or you can also calculate del E by del theta or del E by del phi. You are going to get the same answer, and if you do that, you get this result. This is basically taking a derivative here, and once you get this, time period is proportional to e to the power minus 2 by 3. Okay. Of course, absolute value of e to the power minus 2 by 3, and e is proportional to the semi major axis. So, finally, you get this Kepler's law here, and remember, for all this calculation I have just used action angle variables method. We have not solved the rest of the problem. Of course, I am going to urge you people to go ahead and solve the remaining problem of this, write down the complete Hamilton's characteristic function and calculate the corresponding corresponding canonical variables for each one of the canonical variables will be called as angle variables here. So, calculate all three angle variables here and complete the problem. But the power of this particular method for periodic systems is in calculating frequencies, and this is what we have demonstrated just now. Okay. So, now we have come to end of what I will call as particle dynamics. Okay. In the next week, I am going to start with the continuum mechanics. We just have 1 week. I am going to introduce the ideas of the continuum mechanics, and then we will stop there. But before that, I will briefly recap what we have done in last 7 weeks. See, we started with a simple idea. Newtonian mechanics when written in a coordinate form is not a very wieldy thing, not a very useful as far as problem solving is concerned, especially with constraints thrown in and all that. Remember, the constraints are not one of our really main concerns, but the coordinates are. So, then we derived this Lagrange's formulation, which makes the formulation coordinate independent. What I mean by that is, when you go from one set of coordinates to another set of coordinates, I still get the same differential equations or same Lagrange's equations. And then we expanded that to a very beautiful principle called as Hamilton's principle, which gives us very neat principle that nature takes the path of least action. And then from there we did Hamilton's formulation. Remember, the Hamilton's formulation opens new gates in problem solving or in understanding the structure of mechanics. There is a phase space underneath. We can actually see the phase space portraits. From there, you see, in Lagrangian formulation, the great advantage was it was independent of which coordinate system you use. But in the Hamiltonian formulation, we have a greater freedom. You see, now momenta and coordinates, they are on the same footing, and when I am making transformations, I need not just restrict myself to transformations among coordinates. I can now mix momenta and coordinates and create new variables. And what will I call them? Momenta or coordinates? That is actually irrespective or irrelevant at this point. Remember, momenta and coordinates, they are on same footing, and in fact they are together called as canonical variables. So, we do not make a distinction between the two. And then the canonical transformation again tells you that you can actually do lot of things with transformations between P and Q and solve problems. Okay. And then there was a Poisson bracket formulation. Remember, Poisson bracket formulation is really useful because that also will tell you how to do the canonical quantization procedure to quantum systems. And finally, this beautiful idea that it is possible to sit in one coordinate frame or one set of canonical variables in which you would probably be in some sense moving with the system, so that the system in phase space will appear stationary to you. Okay. And that is finally encoded in this week's topic, that is Hamilton-Jacobi theory. Okay. So, I will stop here and we will see you next week.